Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we are going to be working on an example where we are going to be applying the the new concept that we learned recently, the concept of conditional expectation. And in addition, this example is, I really like this example because we also have the opportunity of revisiting some of the things that we have learned over the semester. You'll see, it's a really nice example. I really like it. It's gonna be fun. Let's begin. So, take a look at that slide, at the statement of the problem that we're trying to solve. Okay. Got it? So, can you see that now what we have in this problem, in this example, is a combination of several of the topics that we have already talked about at this point. Okay, so first step to solve this kind of problem, let's try and translate the information that we're given, right? So first, let's write down the definition of each of these random variables. So example. So y, let's see. So y represents the number of bacteria per cubic centimeter, okay, in liquid, okay? Okay, so note that since y denotes a number, that's going to be, it could be 0, 1, 2, 3, or 1000, right? Okay, so the possible values for that random variable y are going to be integers and 0, positive integers and 0. So we have number of bacteria per cubic centimeter. Okay. Okay. Now, it turns out that y has a Poisson distribution with parameter x. Okay. Okay. So what we have here is that f of let's write that down, right? That y given x, right? Let's use this notation, right? Let's use our notation of conditional probability mass function in this case, because it's a discrete. So the probability of y given x will be an Poisson, right? Poisson with parameter x, right? Okay, so give me a sec because I'm going to find that table in your textbook. Okay, so you can see you don't have to memorize these probability mass functions, these expressions. So in this case, we know that the Poisson would be x to the y power e to the negative x divided by y factorial. But again, I want you to remember where you can find them in your textbook. So give me a sec. Okay, I'm back. So again, if you go to page 837, you're going to be able to find these common continuous and discrete distributions, right? So for this one here, in this example, we're interested in a Poisson random variable, right? And what we have is that a Poisson with parameter lambda, the expression for the probability mass function of Poisson would be lambda to the power y e to the negative lambda divided by y factorial, and the possible values 0, 1, 2, up to infinity, right? So what we have here is that conditional, because again it's conditional, what we know is that you know, it's variable. That lambda is no longer a lambda, we're using an x, but it depends, it varies, it's not a constant, so it will be x to the power y instead of lambda, and then we have e to the negative x divided by y factorial. Okay, and that expression is valid for you know, y equals 0, 1, 2, so on. Okay, let's keep going. Let's go back to this problem. Okay, now as we can see, right, that's what I was mentioning, that x is a variable itself, right? And it turns out that it has its own probability distribution. It has an exponential distribution with parameter beta. Okay, so here we go. What we have here is that x, well, f of x, right, has an exponential distribution, right? And if we go back to our table, then we have to go to page 838. There's where you will find the continuous distributions. The PDF of an exponential with parameter beta is 1 over beta e to the negative y divided by beta. Okay, so if beta equals 1, we are just left with f of x equals e to the negative x. Okay, so e to the negative x, and that expression holds, is valid for positive x, right? Those are the possible values, right? Okay, nice. Now we have translated this information here. Now let's do part A. First step, they want us to find the joint probability function of x and y. Okay? Okay. So our first task is finding that joint. Okay? Note something interesting here, right? We have that conditional PDF, and we have this, you can think of this guy as a marginal. This is the marginal of x, right? And then we go, by definition, the conditional PDF is just what? The joint divided by one marginal. So joint, in this case, it would be the joint of x and y divided by the marginal of x, right? That's just by definition. But then, since we want the joint and we have these two guys, we just solve for this guy, for the joint. We just multiply by f of x on both sides by the joint of x, by the marginal of x, and then we get the joint. Make sense? So let's do that. Just multiply these two guys. So the joint in this case is just going to be this times this, which is just, x to the power y e to the negative 2 times x, right, divided by y factorial, and then it's going to be valid for these values. The y's can be, well, the y can be 0, 1, 2, up to infinity, and x just, positive. So let me just write this down. Right, and let's just say that this is going to be valid for these y's and positive x. Make sense? Okay, part A done. Okay, let's take a look at part B. Part B, we have to find the marginal. Okay, marginal of y. B, let me write that down. What we want is the marginal of y, right? Marginal of y. That's what we want. Okay. Okay. So, first, before we do anything, let's pay attention to this. To this particular joint and to these values that it can assume. Note that probability, that joint probability function is continuous with respect to x and discrete with respect to y. Okay, so since this guy is continuous with respect to x, we know that if we want to find the marginal, we have to, in this case, integrate with respect to x, because it's continuous with respect to x. If, on the other hand, we wanted the marginal of x, since the joint is discrete with respect to y, we would need, instead of using an integral to find the marginal of x, we would need a summation. Okay, so just be careful with that. That's why we have to pay attention to these values, the support, we call it. Okay, anyway, so in this case, we integrate from negative infinity to infinity the joint with respect to x. Since we want the marginal of y, we integrate with respect to the other one. Okay? Okay. But in this case, we know that it's going to be 0 elsewhere, right? This is the non-zero part, and f of x, y, if we want to be super specific here, what we have to say is that the joint will be 0 otherwise. So the only part that matters is from 0 to infinity, the non-zero part. Okay, so let me write that down. We want the integral from 0 to infinity of this guy. This is our joint, and we want to integrate that expression with respect to x. Okay? Now, that y factorial looks scary in that integral, but once we realize that we are integrating with respect to x, this guy is a constant. So we get to factor it out. So that's what we're going to be doing next. Okay? So we have 1 over y factorial times the integral from 0 to infinity of, we are going to only have x to the y power times e to the negative 2x with respect to x. And again, it looks kind of scary at first, but then we realize, oh, y is constant. I mean, this guy y is constant because we're integrating with respect to x. Now, it looks kind of ugly still, but then we go, I've seen something like this before. So let me refer to that table again. Then we go, oh, yeah, that guy looks like a gamma random variable. That's a PDF of a gamma, right? So I need the variable to the something minus 1 e to the negative variable divided by something, and those two guys, alpha and beta, are the parameters of a gamma distribution, right? So this one done. The beta, we already have it. We can see from here that beta is going to be equal to 1/2. This one, we almost have it in the form that we need. Let's just make it be super explicit, super specific. So this is the same x to the power y is the same as x to the power y plus 1 minus 1. Agreed? And there we go. So alpha would be y plus 1. Remember that y is constant with respect to x. So it's going to be a constant. And then we said that beta would be 1/2 in this instance. So if we want to have a true, a legit PDF, we need that constant. And the constant that we need would be 1 over gamma to the alpha times beta to the alpha power, right? Let's make sure. Yeah, that's the one we want. Okay? So in this case, alpha, as you can see, from what we did, is going to be y plus 1. Oops. Beta is going to be 1/2, and since alpha is y plus 1 is the exponent that we need here. Okay, now this is a constant, but I'm dividing by something here inside that integral. So in order to make it legal, I will be multiplying by this guy outside that integral. So that would be just multiplying by a 1, and that would be something legal, right? Not doing anything illegal. There's nothing wrong with multiplying by a 1. Okay, but now again, take a look at the expression of the PDF of a gamma. These are the this is the region where the gamma is non-zero, so we are integrating from 0 to infinity. This is a legit PDF. So this kind of nasty looking integral is just going to be a beautiful one, because it's you know, it's the integral of the PDF of a gamma, and it's a legit PDF. So the integral from 0 to infinity of a gamma, that's just a 1, right? So we're only left off with this times 1, which is just that. Okay, Now, and that's why I said this example is really nice. We get to revisit a bunch of things that we have learned before. Remember that we talked at some point about the gamma function, and we said if you evaluate the gamma function at a positive integer, gamma at n equals n minus 1 factorial, right? Y is an integer, and since we have y plus 1, we're going to have a positive integer. So this guy here, gamma evaluated at y plus 1, is an integer. That means that gamma evaluated at y plus 1 is just y factorial. And that's great, because then what we have is y factorial divided by y factorial times 1/2 to the power y plus 1. Agreed? Yeah? And here, just let me remind you, right, that let me write it down like this. Gamma at n, n equals n minus 1 factorial for positive n, for a positive integer. Okay, that's what we're doing here, using that property of the gamma function. Okay, so anyway, in the end, what we have is the marginal of y is just this. But we also need the possible values, and the possible values are 0, 1, 2, so on. Now it's really reassuring to see that kind of expression, because we go, okay, we know that if we have a legit probability mass function, because this guy is discrete, then if we do the sum for all positive values of the PMF, we should end up with a 1, and that's the case here, because that would be y to the 0, y to 1/2 to the y plus 1 power when y is 0. That's just 1/2. The next one would be 1/4, 1/8, and so on. That would be the sum of 1/2 plus 1/4 plus 1/8 plus 1/16, and so on. And we know that the that series converges to 1, so we're good. That's a legit probability mass function. Okay, so that was part B. Let's do part C. Okay, we want the expected value of y. So the expected value of y would be what? We can use the definition, right? So let's do that. So expected value of y, it would be the sum for all y's. In this case, y goes from 0 to infinity of y times the probability mass function times this guy here. Got it? Okay, so note that when y equals 0, the first term is 0, right? So we start doing this at y equals 1. Okay? Now note that 1/2 to the power y plus 1 is the same as this. To the power y times just 1/2. But then let me factor out that 1/2. Okay? Okay. Now, next, we would like to find, we want to find a value to which this series converges, right? And this is one way of doing it, and that's why it's important to bear in mind those expressions for probability mass functions and PDFs. You have seen something like that before. See the expression for the probability mass function of a geometric. So if P were 1/2 here, the probability mass function would look like this: 1/2 times 1 minus 1/2, 1/2 to the power y minus 1, and the possible values for the geometric are 1, 2, 3, so on, right? Okay. Values from 1, 2, 3 up to infinity, check. But what we need is 1/2 times 1/2 to the y minus 1. Guess what? 1/2 to the power y is the same as this, right? Agreed? Okay, let me copy paste this. I'll place it here, and then I leave this here like that, just so you can see this step by step. 1/2 to the power y is the same as 1/2 to the power y minus 1 times 1/2, right? It's the same thing. But now this thing here, as we said, that corresponds to the probability mass function of a geometric with parameter 1/2. 1/2 times 1 minus half to the y minus 1, right? Possible values 1, 2, 3 up to infinity. So we have y times the probability mass function of a geometric. That's the expected value of a geometric, right? And using that table, what we have here is that the expected value for a geometric is 1 over its parameter p. So what we have here is this last expression here is 1/2 times one over 1 over 2. And again, this is because when you look at this is a probability mass function of a geometric with parameter 1/2, and this is y, and you're doing the sum for all y's of y times a PMF. That's expected value of y, and y has, in this case, we can think of this as a geometric random variable, and the expected value of a geometric random variable with parameter p is 1 over p. In this particular case, p equals 1/2. So what we have here is 1/2 times 1 over 1/2. Guess what? That's just 1. Okay, make sense? Now let me show you something. Remember that at some point in another video we talked about the conditional expectation. Let me find that slide for you. I think it's 130. Okay, remember that we talked about this? So let me show you a way of using that result to double check that we're right, that we found the right expected value. So let's say that another way. Using that theorem, right? Okay. So we want the expected value of y. Okay? Let's use that theorem that you have here. So expected value of y would be the same as the expected value of y given x, right? So we're just kind of plugging in. Okay? Make sense? Let's do that. Let's write that down. Expected value of y is going to be the same as the expected value of y given x, according to that theorem. Okay? So first, let's see. What would be the expected value of y given x? Since y given x is a Poisson with parameter x, we can check our table. Poisson with parameter lambda, mean lambda. So a Poisson with parameter x, mean must be x, right? X, right? And again, this is just because of this. We're told that y given x has a Poisson with parameter x. So Poisson with parameter lambda, mean lambda. Poisson with parameter x, mean must be x. And then we take the expected value on both sides. And we go back to the statement of the problem, and we are told, hey, x has an exponential with parameter beta equals 1, right? We know that from, again, from the statement of the problem, and I think this was slide 132. Yeah. So x has an exponential distribution with parameter beta equals 1. Then we go, okay, let me check my table. If I have an exponential with parameter beta, mean beta. So if I have an exponential with parameter beta equals 1, expected value of x must be 1. So we ended up with the same answer as this, right? But in this case we did it very quickly. See that we didn't get, we didn't need the marginal of y to find this. We didn't need to use the definition of expected value to find this. So anyway, that's an application of that theorem we talked about. Okay, let's finish this problem. We have parts D and E. So now what we want is to find the conditional distribution of x given y. Okay, so here we go. Conditional distribution of x given y, right? So that's what we want here. conditional distribution of x given y. Okay, so what do you think we're going to do? Well, we're going to be using the definition, right? F of x given y will be just the joint divided by the right marginal. In this case, the right marginal would be the marginal of y, and we already have that guy. Right? That's the marginal, and the joint, we already have that from part A. So we just divide this by the marginal, okay? And that's it, okay? So let me show you that, right? Let's do that. It would be this guy. Divided by marginal. This is our marginal. So once we do the math, we just end up with something like this. Okay? We're going to have 2 to the power y plus 1, then x to the power y, e to the power negative 2x, and in the denominator we're going to have a y factorial, and the possible values are going to be x must be positive and y could be 0, 1, 2 and so on. Make sense? Okay, so that's our conditional. The other conditional probability distribution. Note that again we have to, in this case, right, you have to give me y and then I'll know what this expression looks like, and you'll see in a minute that that makes sense. So now what we need is we need to find the conditional expectation of x given that y is 0. Okay, so here we go. Expected value of x given that y equals 0. First, note something. Note that we're going to be doing this. First we find the right conditional given that y is 0. Okay? If y is 0, we have 2 to the 0 plus 1 power x to the 0 power e to the negative 2x divided by 0 factorial. Okay? I'm going to be super specific here. I'm going to be plugging in. Okay? So in the end, at first it looked kind of scary, right? But once you have the y that you need, this just turns into 2 times e to the negative 2x, right? Okay. And then we want the expected value. of that expression. I'm going to show you a lazy way, and then I'm going to show you another way of finding this. The lazy way, I'm a lazy guy, right? Okay, so when I see something like this, I go, I've seen that kind of expression before. This guy looks like an exponential with parameter 1/2. Let's take a look. Let's go to our table. Exponential 1 over beta e to the negative y divided by beta. So if beta were 1/2, I would have 2 e to the negative 2 times x. Nice. That's exactly what I have here, right? So let me just say that. Looks like the PDF of an exponential with parameter beta equals 1/2. Therefore, if I want the expected value of a beta with parameter 1/2, that's going to be 1/2, right? So what I'm saying is that this expected value is going to be 1/2. End of the story, right? Okay, now let me go to your lecture notes and show you another way. I think that must be, yeah, 139. Okay, so first, just like before, we found the conditional PDF, but in this case we just used the definition of conditional expectation. Hey, if you want a conditional expectation, in this case the expected value of x given y, then it's the integral of x times your conditional PDF. And in this case, what I did was noticing that I could complete this expression inside that integral as gamma PDF, and then I ended up with the same result as I did before, 1/2. So two different ways of finding that expected, that conditional expectation. One, paying attention to the expression of the conditional PDF. Another one, just using the definition of conditional expectation, which is, hey, you want the conditional expectation of g, where g is a transformation, a function. Well, then it's, the expected value. In this case, it would be the integral of g times the conditional PDF. Okay, so we're done with this example. I think it was really nice. It's helping us to review a bunch of concepts that we have used before, applying ideas that we have discussed together over the semester. Okay, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.